Hi, everyone. So we are going to do now lesson 37, hypothesis tests for sigma or sigma squared. You remember them? Population standard deviation or variance. Are they here? Oops. Are they here or somewhere else? Okay. The reference reference values here, right? The null. Okay. Assumptions. Now remember that these tests are not as robust as before, right? We really are assuming normality. We have to assume normality, basically. It's not quite the CLT stuff we did before, even with large sample sizes. Now, we're going to deal now with a chi-square test statistic. And remember, that's why, because this distribution, or these distributions, lacked what property? These distributions are not what? They're not symmetric, or they're asymmetric. Okay, in part, that's because sigma and sigma squared are never negative. Chi-square values are never negative. It's kind of helpful they're called chi-square values because they're never negative, right? Squares of real values are never negative. Okay, and also, because we lack symmetry, it means that the p-value method is awkward if you have a two-tailed test. All right, anyway, the chi-square test statistic for tests for sigma or sigma squared, the underlying theory is basically the same for these two guys. All right, so chi-squared equals, it turns out to be the quantity n-1, which is, by the way, the number of degrees of freedom. That's not quite a coincidence. Right? Times s squared over sigma squared, where sigma is, of course, obtained under the null. It's the reference value. The hypothesized value for sigma squared, or the variance, under the null. The null could refer to either the population standard deviation or the population variance. If the null refers to the population standard deviation specifically, you would square that reference value. Again, we use the chi-square distribution on n-1 degrees of freedom. Notice it's been n-1 so far for both chi-squared and t. Okay. Example. And this sounds like a comedy, especially from the 80s. A women's college goes co-ed. So it's a college that has had a long history of admitting women. It's been only women, but after some point, it admits men as well. Now, because of the long history of the college and the students have all been women, we assume that women's heights there have a standard deviation of 2.5 inches. And that's known, all right? That's the known population standard deviation for women's heights. Okay, now the men, they're kind of new. So we don't have the health statistics on the men that we do for the women, all right? I know that we're kind of assuming that the situation hasn't changed over time, but let's ignore that. Let's say that we know the deal with the women, all right? We know the population parameters for the women, like the population standard deviation. But the men are new, and we're not as sure health-wise what's going on with them. Okay, health or medically wise. Okay, so assume that the men's heights are approximately normally distributed. So we'll at least make that assumption. And remember, we needed that assumption in order to even apply the methods of this lesson. And not to say that it's totally okay for you to assume something just so that you have the right to use a certain procedure. But let's assume that genuinely, yeah, men's heights are about normally distributed. We randomly sample 20 men. And let's assume that we have a lot of men who have been at the college recently. Because remember, if little n is too close to big N, then some of these formulas have to be adjusted. Okay, the sample standard deviation for the men now, is 3.4 inches. So that's our value for S. Now, this is sigma for the women, right? I guess you could look at it that way. You could think of this as sigma for the women. All right, and that's known, but we don't know yet sigma for the men, right? That's what we're testing for. Okay, so we randomly sample 20 men, and by the way, 20 is going to be the value of n, the sample size. Okay, and here finally the sample standard deviation. Sample standard deviation is going to be 3.4 inches. A variance, by the way, would be measured in square inches, although that might be a meaningless unit in the context of things. So that's one reason why we might prefer standard deviation in general, because it has quote-unquote normal units. It is true we might deal with variances sometimes, but one drawback to variances is that the units are often meaningless. Okay, test the claim that men's heights and women's heights at the college have different standard deviations at the 0.05 significance level. So I don't know, perhaps there might be dorms, maybe the dorms are still separated between men's dorms and women's dorms. Maybe they're doing like measuring heights of doorways or something like that and wondering what the variance, what the spreads might be, right? Anyway, okay, as far as rounding, oh, by the way, the 0.05 is then alpha. I use red here. 0.05 is our alpha, which was standard. Rounding instructions vary, but here, let's round off to 5 sig figs or significant digits, except round off the chi-square test statistic to 3 decimal places. On an exam, I would tell people how to round. I mean, I don't want you to leave this class thinking, oh, it's all rounding. That's kind of boring. All right, anyway. So use the traditional or classical method of hypothesis testing. So I will tell you what method to use, right? I might ask you to use 2 or 3 methods, right? Traditional, p-value, confidence interval. Use the traditional or classical method of hypothesis testing. And as I mentioned earlier, because we lose symmetry in the chi-square distributions, then we tend not to use the p-value method for two-tailed tests. So I would never give you a two-tailed test in this situation where I tell you to use the p-value if we're dealing with a chi-square distribution. Then we really want to use the traditional method, or maybe the confidence interval method. And here's some hints. Bear in mind, the sample size was 20, right? And it's 20, so we're going to use the chi-square distribution on 19 degrees of freedom. I wouldn't trick you there. Chi-square distribution on 19 degrees of freedom. Here's the density curve. Remember, it's asymmetric. It is not symmetric. The possible values do not go to the left of 0. Here's the density curve. It turns out these will be the critical values. These will be the critical values that trap 95% in the middle for a chi-square distribution on 19 degrees of freedom. So I think we're going to see these things later on. Okay, let sigma be the population standard deviation for men's heights at the college. Now remember, I told you that in the long and storied history of this women's college, we're assuming that the population standard deviation for women was known to be 2.5 inches. We're assuming that that's known. The men, we're not so sure about. Okay, but we're going to let sigma, which is really unknown here. If you wish, you might even want to call this sigma sub men, if you wish. Let sigma, or sigma sub men, be the population standard deviation for men's heights at the college. Granted, this might be kind of awkward to put into formulas. Okay, the methods of this lesson apply because remember, we assumed that the men had about a normal distribution. Or at least you accept that, right? Maybe you assume that and say in your paper, let's assume a normal distribution, roughly. Or not too roughly, but close enough. Here is the setup. All right, let's talk about this. Test the claim that women's heights and men's heights, test the claim that men's heights and women's heights at the college have different standard deviations. Now, there's another way of framing this. Okay, now this is the claim. I'll circle this. Running out of colors. What, turquoise? All right. Not. Orange. Okay, test the claim that men's heights and women's heights at the college have different standard deviations. I'll star it. So that on a final exam, if a student's really running out of time and doesn't have the time to write this out, I might tell the student, you know what, do this. Circle it, star, put star, do a copy paste idea. If you're rushing, right, there's like 10 seconds left in the test. Anyway, now there's a way of reframing this, right? So how can we think about this in terms of sigma, or maybe sigma sub men, right? Sigma is sigma sub men. Sigma sub men is what we're calling sigma, okay? Now, the claim here is that men's heights and women's heights have different standard deviations. So the claim here is that sigma is not sigma women, which was 2.5 inches. Sometimes in a problem like this is a red herring. You don't use this number in the problem. But it might be just a point for comparison. But here, yeah, actually, we do use the 2.5 here. All right. And that's the claim. Sigma is not 2.5 inches. Is this going to be the null or the alternative hypothesis? This does not include the case of equality. In fact, it's the only case that's excluded. Yeah, this got to be the alternative. That's the claim. And it's a claim based on the wording, right? Claim based on the wording. The claim is that sigma is not 2.5 inches. The null is that sigma equals 2.5 inches. And that is absolutely the case. There's no this stunt or that stunt. There's none of that. The null says, absolutely, sigma equals 2.5 inches. It doesn't represent anything else. Sigma equals 2.5 inches. So what kind of test is this? We look at the alternative. Number line for sigma. I mean, it stops at 0, but okay. Which tails will the alternative favor? The alternative likes both the right tail over here and the left tail over here. Now, bear in mind, the left tail stops at 0, fine. But it's a two-tail test because both higher and lower values for sigma favor the alternative. The null is stuck with sigma being 2.5 inches. The null covers very little territory. However, the question is, can we reject the null? That's the thing. Even though the null covers only this sliver here, technically, still the question is, do we reject the null or not? Okay. We now identify the sample statistics. And we talked about these before, right? I mentioned that up here. And it's good to label these things so you don't have to keep rereading the problem. Okay, the sample size, n, equals 20. There are 20 men, and we measure their heights. We want and we need to use the chi-square distribution on 19 degrees of freedom, which means that my hint was helpful. The sample standard deviation for the men, right? I mean, the women, I don't want to say we don't care about women, but we're assuming that we already knew the deal with the women, right? That the sigma historically has been 2.5 inches, and we're assuming that's still good. It's like the ice cream problem, right? Okay, the sample standard deviation for the men that we've measured for their heights, S equals 3.4 inches. So let's compute the chi-square test statistic. Here's the formula I gave you, I showed you, all right? N minus 1, the number of degrees of freedom. 20 minus 1 is 19. S is the 3.4 here, all right? And that's squared, right? S is 3.4, that's squared. Remember that if I were to give you the sample variance, you just stick it in without squaring. So remember we have S squared here, okay? If I give you the sample variance, plug it in for here, right? That is the sample variance. But I'm giving you S, right? Basically, you recognize this as S. So the 3.4, that is squared in the formula. Over, okay, sigma squared. Well, again, it's that same idea, right? Remember, we're assuming that the null is true, right? We're doing these calculations under the null. Do this in green. Do calculations under the null. We're doing calculations under the assumption the null is true. The null says sigma, the population standard deviation for the men, for all the men going to the college, is 2.5 inches. Sigma alone. So sigma is 2.5, but that's squared. Bear in mind that if the null had been framed in terms of population variance, then you would stick it in without the square. To square or not to square depends what I'm giving you, and it depends on what you see in the formula. Work this out, and it's about 35.142 to 3 decimal places. So this is a nice single number that describes how the sample relates to the null hypothesis in the context of this overall test. Okay, 35.142. But looking at it, this may not mean much to you. This may not mean much to you. So it would be helpful to look in terms of either probabilities and p-values, or just ask yourself, so how do I classify this? I mean, is this too extreme or not? I mean, am I gonna, basically, how do I make my decision? Do I reject the null or not, right? How do I determine that? Do I reject the null or not? We're going to use the traditional or classical method to make a decision about the null. Okay, so here's the hint, right? Chi-square on 19 degrees of freedom. Alpha was 0.05, remember, and it's a two-tailed test. So this picture is totally appropriate. And of course it is. I'm not going to trick you, right? But as I said before, I might give you a multi-part problem with multiple hints. So do figure things out. All right, so what are the critical values that trap 95%, okay, which is the complement of alpha? Alpha is 0.05, right? 1 minus alpha in the middle, like for a confidence interval, okay? It's going to be the 8.907, that's the left critical value, and the 32.852, that's the right critical value. They don't go plus or minus like they did for T or Z. Okay, so I'm giving these critical values, and I'm also giving you the critical region. It's in 2 parts. So we have a piece of the critical region over here, and a piece of the critical region over here. So how do we make our decision? Well, here's the critical region. Is the test chi-square value in the critical region or not? Is it in there or not? And remember the deal. It was this here. Okay, well, and let's, as a reminder, as a two-tailed test, we need 2 critical values. This over here is chi-squared sub L. This here is chi-squared sub R, left and right critical values. Okay, chi-squared R and chi-squared L are the critical values, right? The chi-square values that are more extreme than the CVs make up the critical region, and they correspond to the left and right tails over here. I just repeated what I just said. I mean, okay, now the question is, well, is the test chi-square in there or not? The test chi-square based on our sample was about 35.142. 35.142, look here, 34, what was that? It was 35.142, whatever. 35.142. Look at this. Is 35.142 your test chi-square from your sample? Is it in the critical region or not? It is in the critical region. Kind of barely, yeah, but yeah, it's over here. Okay, so the chi-square value is about 35.142. It is in the critical region. That's the danger zone, the acid bath for the null, or regarding the null. This is the danger zone, or acid bath, as far as the null is concerned. What do you do with the null? We reject the null. Okay, lies in the this lies in the critical region. We reject the null. Is that strong or weak? Is that a strong or weak conclusion? Reject, strong. Will we have sufficient evidence or insufficient evidence to say something? We will have sufficient evidence to say something. It will be a statistically significant result. The final conclusion. We reject the null, so that's a strong result. There is sufficient evidence to say something. Who is the claim? The claim was the, I forgot too, actually. It was the alternative. Okay, I remember. It's the alternative. Okay, so it's like the research hypothesis again. Can we prove the alternative? We're weighing evidence for or in support of the claim that, right? Star. That was the star guy, right? Up here. Way up here. I started, right? Way up here. So if you have like 10 seconds left in the test, teacher, you know what I mean. And seriously, I would, but okay. The alternative is the claim. Okay. So conclusion, put them together. There is sufficient evidence for or in support of the claim that men's sites and women's sites at the college have different standard deviations. So if we're a doctor and you're looking at some data, you're thinking, I'm claiming that they're different, the men and the women, with their different SDs, their different measures of spread, and there is in fact sufficient evidence that you're right. You're a smart doctor. Whether you're a man or a woman, you're a smart doctor. All right. Next up, mistakes. Think about a jury trial. In a jury trial, what do we mean by a mistake in a jury trial when it comes to the verdict? Next time.